Hi, this is Pete Singer. I'm with Semiconductor Digest, and I'm talking to Jim Cannon at Mettler Toledo, and he is the head of OEM Industry segment, who are the manager. And for those that don't know, the Mettler Toledo is a very large company, over $2.5 billion, 16,000 plus employees. And one group within the Mettler Toledo is the Thornton Group. So, Jim, I was wondering if you could just start us off with an explanation of kind of the background of Thornton and how you're involved with the semiconductor industry.
Well, thank you, Pete, and I welcome this opportunity. Yeah, I'll give you a little background. Thornton was founded by Dr. Richard Thornton in 1964. And Dr. Thornton was chairman of electrical engineering at MIT University. And Dr. Thornton is known for having written the most accurate mathematical algorithm to measure ultrapure water across all temperatures. Thornton, we became involved in semiconductor at the very beginning. And in fact, Dr. Thornton and Dr. Light established what the actual value, the resistivity value is of ultrapure water for semiconductor. We became part of Mettler Toledo, the process analytics division in 2001. So that was how we evolved into Mettler Toledo. We have played a role, just briefly, sorry, but we played a role with the semiconductor committees. For example, I sit on the liquid chemicals committee. I'm also on what's called FAO 98, which we're looking at reclaim, reuse, and recycle, which are critical as semiconductor moves forward. So
Okay,
we're involved with all the facets.
Yeah, sure. Well, obviously the semiconductor industry uses a lot of water and a lot of different processes. In fact, I think probably almost every manufacturing step has some water involved, in at least in rinsing or whatever. But what are the things that you are looking for when you analyze the water?
Well, ultrapure water, as you mentioned, I mean, semiconductor is the largest industrial user of pure water in the world. Semi-fabs, countries or cities or towns love to have a semiconductor company, but the water usage is enormous. And ultrapure water, they're starting with their source water, and they have to purify it. And there's an entire water cycle in semiconductor manufacturing. From polish to pre-treatment to polishing, that then goes into the fab as they're laying down the circuits on the wafer. Now those wafers go through numerous rinsing steps in the different what are called the tools, or whether they're doing epitaxy or lithography or deposition or the RCA tool. And all of those, especially what's called the RCA process, which is a cleaning process, uses very high volumes of ultrapure water. And what they want to measure is you want to measure for the contaminants. You want to minimize any contaminants. One would be resistivity. You're looking at the ions in the water because you don't want any ions drying on the wafer because those could undermine circuits. Two is organics. So they're monitoring what's called total organic carbon, TOC, below a part per billion. They're measuring in part per trillion. Another measurement is dissolved oxygen. You do not want to have a high level of oxygen in the water. That can cause problems with the circuits and the wafers when it dries, oxidize the surface. The other is silica. Silica is ubiquitous in the world, and silica is also one of the indicators of the health of your water system. As they use multiple purification processes, and one of them is deionization. They use deionization resin or electrodeionization stacks. But as those resin columns age, one of the first ions that would come off the resin is silica. And silica, if it dries on the wafer, can cause certainly issues with the chips. So in addition, as that moves forward, now you have this large amount of water coming out of the tools for example, the RCA process, that goes into a waste stream. And this is one of the areas we've been working with the committee on, is looking to segregate these waste streams. So can they recycle it, reclaim it, or reuse it? And they want to bring as much water possible back to the purification side to reduce discharge. And to do that, they're going to have to measure some other parameters. They have to monitor things like pH, dissolved oxygen. In some cases, they're going to be ozonating certain processes. So they have to monitor ozone. So this is an entire cycle. It's not just about purifying the water to make ultrapure water. That's critical. And what's very important, as the semiconductor has evolved and we've gone from the smaller to the 300 millimeter wafer, you now have more chips on that wafer. But more critical is as the line width comes down from the 30 nanometer to 20 nanometer, we're now looking at fabs that are moving to 3 nanometers. And when you consider that a human hair is 100,000 nanometers in width, it gives you some perspective. So you cannot have any ions or organics or silica drying on that layer of circuitry they just put down, because as they lay down the next layer of circuitry, those ions that dried in between can cause tunnels or vias underneath, which would short circuit the chip. So that entire wafer then becomes useless. So these are some of the, and we are constantly trying to improve our measurement technologies for resistivity, for TOC, for silica, for sodium, dissolved oxygen. So it's a constant process. And then getting involved with tool manufacturers, because they need to control. I mentioned the RCA process. And just as for those that don't know, the RCA process was actually developed by an engineer at RCA Television years ago. And that's why they call it the RCA process. But it's a cleaning station, and they perform what's called rinse to resistivity. These wafers are in what are called a boat, which is put in what looks like a kitchen sink. And they measure the resistivity and the TOC coming in, resistivity and TOC exiting. And they rinse those wafers until the outgoing equals the incoming. Those wafers are then taken out, they're dried, and they're put into the next step to put down the next layer of circuitry. So it's a constant process. So a wafer today may go through 70 to 90 rinsing steps before that wafer is taken out and the chips are cut out of the wafer. And then, of course, they put them in your phone or tablet and tell you, don't put them in water after they've been put in water 70 to 90 times. Sorry, but that's reality. But what's one of the critical areas, and I brought this up a minute ago, is that for years, these waste streams from the different tools. Now, some tools, for example, the CMP process, chemical mechanical planarization, where they're making sure the wafer is perfectly flat with a slurry, that has a lot of particulate matter in it. Then there's processes that use hydrofluoric acid. That's a pretty ugly acid. And then you have ammoniums in there. You have hydrogen peroxide. And many people are putting all these different waste streams from the tools into one waste outlet. Well, when you do that, there is no way you can segregate that stream. You now just have massive amounts of waste being discharged. So what the industry and the committee is looking at is laying out a real plan for a fab to design how they can segregate the waste from the different tools, so that, for example, on the RCA process, most of that water can be taken right back to the front of a purification process. Now, obviously, your hydrofluoric can't. That hydrofluoric has to be treated specifically. And we have special sensors, both resistivity and pH, to measure the hydrofluoric concentration in a waste stream. But so the industry wants to segregate these streams So example, the waste, the slurry from CMP can be taken to a filter press and not put into the waste stream. The hydrofluoric can be treated specifically. The ammonia waste, which can't be discharged to the environment unless it's neutralized, you have to do that, control that with pH. But by segregating these waste streams, we are working with the industry to bring semiconductor to a point of 90 to 95% reuse of water, which will be a major breakthrough. Um, there are areas, Taiwan, Singapore, Arizona, where the companies are actually being legislated to increase their reclaim percentage. And so this is a major challenge for the industry, but it's a challenge we have to meet. We have to be able to reduce the total water usage from a fab. Now, for years, Semi has tried to look at another, I'll use the word solvent for cleaning, gases, chemicals, whatever. But the reality is they keep coming back to ultrapure water because ultrapure water is the most aggressive solvent they can find. Ultrapure water does not want to be pure. Ultrapure water wants to pull into it anything it can pull in. So that's what makes it such a universal cleaning agent. And as the line widths get less, the quality of the ultrapure water and the measurement technology has to improve. As I said, we're measuring in, for example, TOC. The recommended limit in semiconductor is 1 part per billion. The reality is global semi companies are mostly measuring down in the 0.5, 0.6, 0.3, which is in the part per trillion range. To give you a reference point, in the pharmaceutical industry, the TOC limit for water for injection, the water that's used to make saline solutions, make drugs, that limit is 500. So look at the difference between pharmaceutical at 500 and semiconductor at 1. And the reality is not just semiconductor, Pete. Flat panel displays. All your flat panel displays in the industry, as they lay down their color matrix, every layer has to be cleaned with ultrapure water before they put the next matrix down. So it's not just about chips, it's much more than that. But as we are in this super cycle for semiconductor, which is an amazing ride to be on right now, and we've all seen the news, the new fab Intel is putting in Ohio, Samsung in Texas, TSMC in Arizona, the expansion of TI, Infineon expanding. I can go through a list of these. Semiconductor is in another super cycle. But the limits, because of the line width and the size of the wafers, has gotten tighter and tighter and tighter. And so we at Thornton spend a great deal of time, R&D time, working with Semi, working on the R&D side with them to provide better measurement technology, faster technology, more sensitive and more accurate measurements for the key parameters, which are, as I mentioned, things like resistivity, silica, TOC, sodium, dissolved oxygen, and I can go through a litany of them. So, you asked me what time it was, and I just told you how to build a watch.
Sure.
So,
No. Well, out of all these applications you mentioned where, the feed water and during wafer processing and during the reclaim, et cetera, where are your products actually involved? Is it kind of an inline process, or is it they're using the samples, or how does that work?
great question. Thank you. Depending on the parameter, your resistivity would be measured in line. Why is that? Because the sensor material that we have does not contribute any contaminants to that ultrapure water. So it can measure in line. TOC, for example, though, because on a TOC system, and it's referred to as online, but in general, it's a side stream. Because what's happening is you are taking a side stream, you are measuring. By the way, all online TOCs do not measure TOC. They measure conductivity. So what they're doing is they measure the conductivity and temperature. You oxidize with UV at 185 nanometers. So you're oxidizing the water, you're creating carbon dioxide compounds in there. And then you measure conductivity and TOC again. And that change in conductivity can tell you very accurately the TOC of the water. But since you've done something to that water, that would have to go as a waste stream. Now, dissolved oxygen, because you could have electrolytes in the dissolved oxygen sensor, that would also be a side stream. Now, so in the ultrapure water purification, your resistivity is going to be in line. TOC is side stream. Your dissolved oxygen or ozone will be a side stream, and silica is a side stream. Then you move to the tools. So on the tools, whether it's CMP process, you want to measure the resistivity of the water coming into the slurry and the pH. Those are in line. All right. On the RCA process, where you're measuring resistivity, those are in line also. All right. As you move to your waste treatment, for example, hydrofluoric or ammonium treatment with pH, those would generally be a side stream that you would be pulling out. Because, for example, on a pH sensor, you have electrolytes in there. That's how you measure pH. It's that glass membrane, the bulb. And there's a buffer, an electrolyte inside. So that shouldn't be in stream normally. In some applications, it can be. But so to answer your question, they're used in a whole variety of ways, depending on what that water is going to do or what you're trying to measure and either discharge or reuse.
Okay. And in terms of the actual tools, you had mentioned that there are different types of sensors used for different applications. And I would assume different, that the information is collected and transmitted in different ways as well. I know you have a catalog out there, but I wondered if you could just give a little bit of insight into, what kind of actual hardware you provide.
Certainly. We provide, for example, on resistivity, a variety of sensors. Primarily, the sensor body is titanium, though if you are measuring hydrofluoric, it's a material called Monel, because hydrofluoric will eat up titanium. So that's a type, and certain lengths and certain what are called a cell constant. Conductivity sensor, a pH sensor, if you go back to your first high school lab, chemistry lab, you had pH buffers, pH 4, pH 7, pH 11, and you had to measure the slope of a pH sensor. But conductivity is a physical measurement. It's the length and area of the sensor. So the sensor has a physical constant. Generally, the physical constant is 0.1 centimeter squared is what it is. So we have a variety of those. But we also have, for example, a sensor that has a cell constant of 0.01. Now that's used for pure alcohols and pure glycols because those have a different resistance curve than ultrapure water. And so they use a different sensor. The TOC is fairly, it's really sort of one version, and it depends on whether you want an inline or a portable. Ozone, we have both polarigraphic and optical for dissolved oxygen. For ozone, there's one version, and sodium is a single version. Now, those sensors. So if I have for example, if I want to monitor resistivity, I want to monitor TOC, and I want to monitor dissolved oxygen on my ultrapure water skid. So I have three sensors. All three of those sensors can be connected to one of our transmitters. One of the things Thornton introduced back in the 1980s were transmitters that were multi-parameter, multi-channel. So you can take one transmitter and you can connect 4 different analytical parameters. You could have 4 resistivity, you could have 4 TOC, you could have 2 resistivity, 2 TOC. That information goes to the transmitter. That transmitter will display each channel that you want to look at, or all channels at the same time. And that information is then transmitted by a variety of methods, things like analog output, Ethernet, Modbus. How does the end user want to see their data, right? Because they are going to set limits, they're going to set alarms or notifications if they see any trend. And what we do, we work with them to look at the trending of the data. As I talked about silica. Silica is on an ultrapure water system is used really as the canary in the mine. It tells you the health of the deionization resin or the electrodeionization stack. And that way you can prevent silica breakthrough or what's called a silica dump. Because as the resin starts to reach exhaustion, it will all of a sudden let loose the silica, which has one of the least affinities to stay on the resin. And you don't want that. If you have that dump into your ultrapure water, it goes to the fab, you're going to have your yield on your wafers is going to collapse. So you want to monitor that silica real time so that you know when to do preventive maintenance or preventive service on the water system. And all that data then can be displayed locally or transmitted to a control facility at the fab. In addition, for example, we work with we work with all the semiconductors, but one of them has multiple sites around the world, and they actually pull that data from each fab on their ultrapure water in the fab and compare sites in Israel, Ireland, China, US to monitor how the ultrapure water is being maintained and produced at each of the fabs worldwide. So they have a real-time picture of the quality of the water going to the fab, which is critical for this production because these facilities are going 24/7. And obviously now, if you tried to buy a car, you know why. A little shortage in chips.
Yeah, and we've hearing a lot about smart manufacturing, and obviously this is a key part of it, and collecting the data and analyzing the data and comparing it across the fabs. So that's interesting to hear. Okay, Jim, well, we've covered a lot of ground, and it's been almost a half an hour, which is great. Any final comments on key takeaways from this?
Well, I think the key takeaway, and one of the things we tell not only the fab, but the system fabricators that build water systems, more measurements don't give you better water, more measurements give you better control. And if you are measuring real time and know what you're looking at and work with Thornton to analyze your data, we can help you assure that your ultrapure water, the water to the tools, and your reclaim water is of the highest quality possible. And I would welcome anyone if they want to reach out to have questions answered on different parameters. We're always available, and we spend a lot of time providing that support to the industry.
Okay, well, thank you, Jim, and hope you have a great day.
Hey, Pete, thank you. Thank you for your time. I really appreciate the opportunity. Take care.